Good morning.
Good morning, ma'am.
Yesterday, Sanjit Kumar and Divam Agasthi has given the answer, and another person also given the answer. I forgot his name. Who was he? There were the three person who were giving the answer.
Ma'am, roll number 44.
Roll number
44.
42. No? Okay.
44, ma'am.
44.
Yes.
Okay. Today we will start the entropy principle. This entropy principle is also known as principle of increase of entropy. Okay. So what is that one? Entropy principle means in this case we will discuss for the isolated system. In that case, your entropy will never decrease. Always it will be in increasing condition, and that entropy will be the maximum at equilibrium condition when it will achieve the reversible process. Okay, so that is your entropy principle. So we will derive or we will see it by using the equation. So all of you know that any infinite um, um, process, in that case we are having ds is greater than equal to dq upon t, right? So far we have discussed this equation. So for any infinitesimal process, ds will be greater than equal to dq upon t. So if it is the isolated system, in that case dq will be 0. Okay. So in isolated system, there is no mass transfer as well as no energy interaction in the across the boundary. So here the energy is the heat transfer. So dq will be the 0. If dq will be 0, then this term, this equation 1 will be your ds greater than equal to 0. So this is for the isolated system. Okay, so if we will break this equation, then it will look like this: ds iso is equal to 0, and another one is the d iso that is greater than equal to 0. So in this case, this will be applicable for the reversible process, and it will be applicable for irreversible process. Okay, so this ds iso is 0 means if you are taking the integration of it, then it will give the s iso is your constant. That is, your entropy will be constant. In case of your reversible process, it will be maximum when it is a constant mean it is it is also the maximum point at which there will entropy will remain constant. Okay, so this is if you will observe these two terms, we can conclude that for the um, isolated system, it will always in increasing condition when your process will be irreversible one, and it will be become constant and maximum at the equilibrium position, that is at the reversible process. So it is the principle of increase of entropy. So sometimes this isolated system, we will take it is a combination of the system as well as your surrounding. So sometimes this system and surrounding combinedly, we will also we can also tell it as the universe. Universe. Okay. So suppose I'm writing the entropy transfer in the universe, then it is a similar concept like your entropy transfer in isolated system. So this can be the entropy transfer can be the greater than equal to 0, similar in case of your isolated system. So this universe, we can write it as it is the additive property. Additive property means in this case entropy of the system and entropy of the surrounding both will form as entropy of the universe, in which the addition will be always greater than equal to 0. That means it will be constant in case of the reversible process, and it can be greater than 0 means it will give you the positive quantity. That means it will always in increasing condition. So whenever you are applying this entropy principle for any problem related to your irreversible or irreversible process. In that case, both terms, that is the entropy transfer in system and entropy transfer in surrounding, both will be considered and both will be added so that your entropy transfer for the universe can be find out. So now we will consider some example. So application of the entropy principle. So there we will use this equation in some problem where we have to find out what will be the entropy transfer or entropy increase. So first, the basic type of example we are considering, if there is the heat transfer to finite temperature difference. So there we will have some reservoir which we will have the different temperature. Both we will have the different temperature if there is a heat transfer from the one reservoir to another reservoir. So what will be the entropy increase or entropy transfer in system and surrounding, that we have to find out. So for this heat transfer to find out temperature difference, let me draw the diagram. In here we will take the two reservoir. One reservoir is your which is at the temperature T1. Okay, so these two will be connected through a rod. This is the second reservoir which is at the temperature T2. So in this case, T1 temperature is greater than your T2 temperature. Okay, so there is the heat transfer from the reservoir R1 to the reservoir R2. So if you will observe in this case, after some times, in this case, due to the heat transfer, there will be the increase of the entropy in this R2 reservoir. Here in this case, there will be the decrease of the entropy. Okay, so uh, finally, we have to find out what will be the entropy transfer in the universe. So both will be added, that entropy transfer in the system and entropy transfer in the surrounding. So if you will observe, these two reservoirs both are connected with the help of the rod. So what will happen in this case? In this case, the entropy change in case of your rod we are considering as the zero. Why? After the transfer of the heat, uh, when your steady state will achieve uh, after some time, so we can say that there is no coordinate change within the rod. So because of that one, in this case, the entropy change we are not considering for the rod. Only we are considering for the reservoir R1 and another reservoir, that is your R2. Okay, so now we can write down our equation for the entropy change. So for the entropy change, we can write as delta S1 for the reservoir R1. So in this case, your equation will be the Q upon T1, right? So in this case, your Q is transferred from R1 to R2. So in this case, your entropy will decrease when your heat is flow out from the reservoir R1. In that case, we will take the negative sign. We will give the negative sign. Okay. So in this case, delta S1 will be the negative, and next is your delta S2. S2 means in this case we are considering the entropy transfer for the reservoir R2. In this case, what will be the your entropy transfer? That will be the Q upon T2. In this case, if you will observe, in this case, entropy transfer will be the positive quantity because the heat is flow into the reservoir. So it will be the positive quantity. So I will put the positive sign. So now we have to write down what will be the entropy change for the universe, that I can write down delta is universe, that is your delta S1. As I've already told you, it will the entropy change or transfer will be added. So here it is for this is reservoir 1 and reservoir 2, and for the rod it will be 0, because after the steady state, there we are considering that there is no coordinate, there is no change in the coordinates of the system. So the properties of the system in the coordinates. Okay, so delta S1 will be the minus Q upon T1, plus delta S2 will be the plus Q upon T2. So it will give, we can take the common Q outside. Then in this case, T1 into T2, This will be the T1 minus your T2. Okay, got my point. So this will be the final term. If you will observe in this case, delta S universe is become a positive quantity. Become a positive quantity means it is greater than 0. Okay, so greater than this will be the become positive quantity, it will greater than 0. So we can conclude that your universe, the entropy will increase in this case. So as we are having T1 greater than T2, then delta S universe will be greater than 0. If it is the T1 equal to T2, then delta S universe will be 0. So this will be the further reversible process. Okay. So this is one example. Next one is your two fluids. Okay. So mixing of two fluids. In this case, also there will be increase of the entropy that we will discuss in this case. Let us consider there is one compartment or one container in which there is the partition. In that container or composite system. So here we are having the two compartment. Here we can say that here we will have the subsystem 1, in this case subsystem 2. So both will comprise of your composite system. So this composite system is adiabatically enclosed. Adiabatically enclosed means here we are providing the insulation so that there will be no energy transfer from the composite system to the surrounding. Getting okay. So in this case, subsystem 1, let us consider we will have the mass is M1. Certain amount of fluid is there that is having the mass m1. It is having the specific heat or heat capacity, that is your c1. Also it is having the temperature t1. This is for the subsystem 1. Then similarly for the subsystem 2, it will have also certain amount of fluid which is having the mass is m2, specific heat is your C2, and your temperature is T2. Okay, so this one is your partition. So this is for the subsystem 1 and subsystem 2. So what we will do in this case, suppose we are removing this partition. This one is the partition. Suppose we are removing this partition. So what will happen? These two fluid will get mixed with each other, and it will obtain the final temperature. That final temperature we are taking it as the TF, small TF. So initially I will not take as a absolute temperature scale. So I'll take a normal degree Celsius, that is your T1 and T2. Okay. So temperature of the subsystem T1, and it is the temperature of subsystem T2. So both fluid will attain the final temperature after the mixing, that is your TF temperature. So in this case, the TF temperature is T1 is greater than TF, TF is greater than your T2. So both T1 and T2 both will attain the final temperature, that is your TF temperature. Got my point? So in this case, after the mixing process, suppose we are considering that the energy interaction between this composite system will be remain same after the mixing. So energy interaction means in this case we can write down that equation, that is your MCP right? MCP means in this case we are having for the subsystem 1 we are having the C1, and for the subsystem we are having the C2. So energy of the subsystem 1 is equal to the energy of subsystem 2 after the mixing of the two fluids. So here I can write that equation, that is the M1C1 into dt, means in this case that will be the T1 minus Tf. Similarly, in this case, it will be the M2C2, that I can write as Tf minus your T2. Okay, Tf minus T2. Got my point? So here I can write as Tf will be, if you will simplify this relation, then we will get M1 C1 T1. Please simplify this one.
Plus M2 C2 T2 by M1 C1 plus M2 C2.
Tf minus M2 C2 T2. Tell me, Tf will be,
M2C2 T2.
I am to C2 plus M1 C1.
all of you got this one, I think.
Yes,
ये
ma'am.
ठीक है ना? Okay. So this is the final temperature which will achieved after the mixing process. Then we have to find out what will be the entropy change in case of the subsystem 1 and in case of the subsystem 2 after the mixing process. So that one I will write down. So we will take the integration, though it is the mixing process is the irreversible process, to get our absolute value of entropy change, entropy transfer. So for we have to integrate. Okay, we have to take the integration. So for taking the integration, we have to assume that this is the reversible process. So in that case, what will be your equation for the subsystem 1? Your entropy change delta S or ds will be whatever it may be. It will be the integration of the T1 to Tf. Here I have taken the absolute temperature scale. Absolute temperature scale means that is your T1 plus 273 is equal to your T1. Okay. So in this case, we will take as M1 C1 dq of uh, dq, sorry, let me erase this one. It will be the dq upon t, right? So if it is the dq upon t, means it will be the ds. So S1 लिखिए. So which I can write like this: T1 Tf M1 C1 dt upon t. Okay. So this will be M1 C1 ln Tf upon T1, right? So we will get this equation. Similarly, for the subsystem 2, I can write this equation, that is the T2 will approach Tf, so which is integration of your dq upon t. So in this case, this will be the T2 Tf M2C2 dt upon t. So it will be the M2C2 ln Tf upon T2. Okay, so this is the entropy change or entropy transfer in case of the subsystem 1 and subsystem 2. Then we have to consider what is the entropy change for the universe. So universe, I can write down the addition of the two entropy change, that is a ds1 plus ds2, because entropy will be the additive. Then this will give us m1 c1 ln tf upon t1 plus m2 c2 tf upon t2, right? So if you will observe in this case, this will be also a positive quantity. That means the entropy change or entropy transfer for this system, mixing system, will be greater than 0. Because in this case, T1 is your greater than T2. Also, the T1 is greater than your TF. So in this case, your delta S universe will be positive. And this will be also
संजीत कैमरा ऑफ कर लो.